It's a very simpler process. So as this part is not permeable for urea anyways, so urea gets concentrated, and when it reaches to this medullary part of collecting duct, there are many urea transporters which absorbs urea, and then this urea can enter into the medullary interstitium, making it hyperosmolar, contributing it to the hyperosmolarity of medullary interstitium. And again, this urea is absorbed by the ascending part of loop of Henle, and then again it is reabsorbed here again. This cycle continues, right? This again, it somewhere contributes to this MIH, which is around 30 to 35%. So this is known as urea cycling, basically. Yeah. And ADH amplifies both the mechanisms of countercurrent multiplier. It is important for, so yes, ADH has a function of amplifying both the countercurrent multiplier systems, which somewhere favors for absorption of water, right? We have this countercurrent mechanism to increase the absorption of water, right? So ADH is also already an antidiuretic hormone, so this will also amplify this countercurrent multipliers. Now let us see how is MIH maintained. Now what happens is, this is vasa recta, right? So the blood flows and then goes back. So vasa recta is the blood supply to the deeper parts of nephrons. So what happens is, when the fluid goes down in the vasa recta, right, so it is permeable to water and solutes, right? As the interstitium is hyperosmolar, it constantly loses water and it gains few solutes, but it majorly loses water, making the fluid hyperosmolar. Okay, now while moving back up, so fluid travels towards the hypoosmolar conditions. So when the fluid moves upward, that is exposing to the hypoosmolar fluid, right? So now it starts gaining water back, right, to make it equal to 300. So it moves upward, it gains water back. All right. So what happens is, it is countercurrent exchanger system. So whatever is lost, and again it is gained, right? Whatever the water was lost, again it is gained, and whatever the solutes were gained, and they are lost while going back, right? So this is countercurrent exchanger system. Okay, there is an exchange going on here. So to understand how is this important right now is, so this is very important to supply blood to every part of nephron, right, even to the deepest part. But if the blood vessel would have been just straight like this, then while moving down, it would have gained all the it would have lost all its water, and it would have gained all the solutes while moving down, right? And this would have led, look here, as it was moving down, it is losing water and gaining solutes, so it have become the hyperosmolar at the end, right? And this hyperosmolar fluid would have just directly joined the vein and would have escaped everything, right? But due to its arrangement in a form with an hairpin bend, now this water it is losing is again gained back, and the hyperosmolar medium is also maintained. So this is why the blood vessel is arranged in a hairpin bend called vasa recta. So this arrangement prevents a wash out of medullary hyperosmolar interstitium by blood flow. And if this part would have been directly connected to the vein, the solutes would have been lost completely. But that it is arranged like this in a U-shaped pattern, so the solutes are lost and water is gained back, and the blood with a similar osmolarity of 300 is connected to the veins, right? Now when we look at this ADH counter-current differences. So it's multiplier, and exchanger. Multiplier is a Lopov-Henle, exchanger is vasorecta. Air diffusion occurs passively, here active transport is being done by sodium chloride transporter, and it generates hyperosmolar and it maintains hyperosmolar medullary interstitium. Now let's talk about this ADH function. So ADH functions occur in the late part of DCT and cortical and medullary part of collecting tubule. So they have principal cells on which aldosterone and ADH work. Aldosterone retains sodium and water, ADH retains water, and aldosterone also does this in the loss of potassium ion, right? So thus aldosterone can enter into the cell, so it has the cytoplasmic receptors. ADH will bind to the receptors on a lipid membrane. It activates G-stimulatory, it activates adenyl cyclase and increases synthesis of cyclic AMP, which activates protein kinase A. This activates the protein kinase that phosphorylates aquaporin 2 vesicles present inside the cell. These aquaporin 2 molecules they get inserted onto the luminal side of membrane and they are responsible for absorption of water. Okay, so they produces concentrated urine. Okay, and we know when detailed function of ADH function has been discussed in previous videos. So now let's know that how this counter current multiplier system, the setup of making medullary interstitium hyperosmolar, how does this actually helps in absorption of water. So as you can see, fluid is diluted, which is entering into this part, right? And this part is having gradient of 300, then 600, then 800, then 1100, 1200, so ever. So what happens is, in the absence of ADH, the 60 milliosmol per liter of fluid will directly leave the collecting tubule without getting reabsorbed, and it produces diluted urine. Whereas in the presence of ADH, what happens that it activates the sodium potassium 2 chloride transporters present in the thick part of ascending limb of Lopov-Henle, and this increases the hyperosmolarity. Okay, and it also activates urea transporter mechanism. All this makes this area hyperosmolar, and when this area gets hyperosmolar, there is an absorption of water through this aquaporins, right? If this area is already hyperosmolar and the fluid that is entering here is hypoosmolar, so this will provides a good concentration gradient, good force that the fluid can move, solvent can move from the lumen into the interstitium. In this way, water is absorbed, producing the concentrated fluid, which is around 1200 milliosmol per liter. Okay, so and in severe conditions where there is an extreme requirement of saving water, the body can produce medullary hyperosmolarity of 1400, so that maximum water can be reabsorbed, making urine concentrated at 1400 milliosmol per liter too. Well, this is done in an extreme case of water dehydration. Anyways, so what happens is, basically this is osmoreceptors present in the hypothalamus, right? And this is the posterior part of pituitary, and it has a suboptic nucleus situated in the hypothalamus, which synthesizes the ADH, and ADH is stored in the posterior part of pituitary. And whenever this osmoreceptors sense that there is hyperosmolarity, so what it does, when there is hyperosmolarity sensed by them, they will activate these neurons and ADH is released. So this work on principal cells, it absorbs water and produces concentrated urine. And this, whenever this osmolarity receptors sense the fluid is hypoosmolar, they inhibit the release of ADH, and then there is no ADH action on the late part of nephron, so urine produced is diluted and less concentrated, basically, right? And in the case of desert rodents, as they were designed to live in desert with least water consumption, they have very long loop of Henle, so that maximum concentration gradient can be created, and which is somewhere around 5,000. Oh, this is so much actually. And more concentration is produced, and the most fluid is reabsorbed back, making the urine highly concentrated, right? And when we talk about this, something called as tubular fluid osmolarity by plasma osmolarity. Okay, so here as you can see, tubular fluid osmolarity and plasma osmolarity is equal, so it is 1, and it is 1 even at the end of PCD. And in this part, as we're losing water, so tubular TF increases, right? Tubular fluid is around to 1200 osmol, so TF by P is usually 4, or it is more appropriate to say that it is greater than 1. And while moving upward, it gets hypoosmolar, right? The tubular fluid is around 100, and the overall ratio of TF by P is around less than 1. And as the in the late part of DCT and this collecting TPO, there can be two scenarios: one in the presence of ADH and in the absence of ADH. So what happens in the absence of ADH? There is no ADH, so tubular fluid is very much hyperosmolar, and it is less than 1. But in the presence of ADH, the tubular fluid gets hyperosmolar due to absorption of water. So as tubular fluid get hyperosmolar, it is more than 1. Okay, and so this is same in the collecting duct as well. So this produces diluted urine in the absence of ADH, and in the presence of ADH it produces concentrated urine. Alright.